Hi everyone. So this lecture is going to be very interesting and important for you. So just be focused uh, and make your own notes, right? So we were discussing about the chi-square distribution. Chi-square distribution. We were discussing about the chi-square distribution, in which uh, we have discussed about the PDF of chi-square distribution, that is equal to 1 upon gamma n by 2, 2n by 2, e raised power minus x by 2, x n by 2 minus 1, where x is greater than 0. So this is the PDF of chi-square distribution with n degrees of freedom, and we saw that if x1 follow normal 0 comma 1, then x1 square will follow chi-square 1. Clear? Now if x1 will follow normal 0 comma 1 and x2 will follow normal 0 comma 1, then x1 square will follow chi-square 1, x2 square will follow chi-square 2, and sum of x1 square plus x2 square will follow chi-square 1 plus 1. So this will follow chi-square 2. Clear? So this is the additive property. This is the additive property of chi-square. Additive property of chi-square. हमें ये देखना है, additive property हम बाद में देखेंगे. Let's see what is this. This is x1 square follow chi-square 1, x2 square follow chi-square 2, and the sum of x1 and x2, which both are following the chi-square with this is 1 degree of freedom, with 1 degree of freedom, then the degrees of freedom of x1 square plus x2 square will add up. That's 1 plus 1. Similarly, you can remember like this: if x follows chi-square m, y follows chi-square n, then x plus y will follow chi-square m plus n. Right? So now the derivation of chi-square. The derivation of chi-square is most important for you. Derivation of chi-square. See, the derivation of chi-square. Let xi, I is equal to 1 to up to so on, yeah, up to n are independent normal mu I sigma I square. Xi is following normal mu I comma sigma I square, and what's chi-square n? As you remember, that is summation n, I is equal to 1 to n xi minus mu I upon sigma I whole square. Or let's write this as summation I is equal to 1 to n, this is ui square. And what's ui? Ui is xi minus mu I divided by sigma I. This is my ui. क्लियर? और ये किसको फॉलो करेगा? ये फॉलो करेगा नॉर्मल 0, 1 को. ये किसको फॉलो करेगा? नॉर्मल 0, 1 को. अगर xi's are independent, can I say so as ui's are independent? क्योंकि ui तो फंक्शन है ना xi's का. ये देखो ना, ये तो फंक्शन ही है ना xi's का. ui is function of xi. If xi is independent, ui is independent. Clear? Now what's mgf of chi-square? if I write this as, let us suppose this is the MGF of chi square. Can I write this as m summation of ui square t? I is equal to 1 to n. Or can I write this as product of m ui square t? This is I is equal to 1 to n. Or can I write this as m ui square t raised power n? How is this? Uh, how is this correct? To see, chi square t is equal to this, as you know, right? So in place of this, can we write this as u1 plus u2 plus u3 plus u4 up to so on up to un t? Is this correct? Yes. तो see, आपने पढ़ा होगा MGF में एक प्रॉपर्टी है, if x follows some distribution, y follows some distribution, then MGF of x is mxt or MGF of y is myt. Then mx plus y t is equal to mxt multiply myt by the reproductive property of MGFs. तो जो एडिशन में होगा वो मल्टीप्लीकेशन में होगा, मतलब इंडिविजुअल MGFs का मल्टीप्लीकेशन होगा. तो वही मैंने यहाँ पे लिख लिया, ये और ये बराबर है, सेम है. तो इसको मैं ऐसे लिख सकता हूँ m uit मल्टीप्लाई m u2t मल्टीप्लाई m u3t अप टू सो ऑन. जब ये मल्टीप्लाई होगा, ये तो यही है ना, प्रोडक्ट ऑफ दिस, ये तो प्रोडक्ट ऑफ इंडिविजुअल MGF से. तो जब इसको मैं ऐसे भी लिख सकता हूँ, these are the n times, these are the n times. MGF तो सेम ही है ना. MGF क्यों सेम है? क्योंकि पहले देखो xi किसको फॉलो कर रहा है? नॉर्मल को. तो chi स्क्वायर किसको फॉलो करेगा? ये xi स्क्वायर किसको फॉलो करेगा? chi स्क्वायर को. तो इनका MGF सेम होगा. x1 का भी MGF सेम है, x2 का भी MGF वही होगा, x3 का भी MGF वही होगा. तो ये n टाइम्स क्या होगा? मल्टीप्लाई होगा. अंडरस्टैंड? ये n टाइम्स मल्टीप्लाई होगा. ठीक है, ये n टाइम्स मल्टीप्लाई होगा. तो सी, अब हम क्या करेंगे? अब देखो, अब हम क्या करेंगे? सी, दिस इज m chi square t that is equal to expectation of e t mu I square. या इसको ऐसे भी लिख सकते हैं, क्लियर? सो अगर हमारे पास डिस्क्रीट होता है तो हम MGF को कैसे लिखते हैं? समेशन ई टी एक्स एफ ऑफ एक्स या पी ऑफ एक्स एक्स dx. dx नहीं, dx इसमें इंटीग्रेशन तो नहीं होगा ना, बट समेशन तो हमने ऑलरेडी ले लिया. ठीक है, अगर अब कंटिन्यूअस है तो हम क्या करते हैं? माइनस इन्फिनिटी टू इन्फिनिटी ई टी एक्स एफ ऑफ एक्स एक्स dx. तो यहाँ पे ये कंटिन्यूअस है तो हम क्या करेंगे? हम तो वही करेंगे, माइनस इन्फिनिटी टू इन्फिनिटी ई टी म्यू आई स्क्वायर, और व्हाट इज द पीडीएफ ऑफ दिस स्टैंडर्ड नॉर्मल जो हमने बनाया है, दैट्स chi स्क्वायर. तो वो होगा कुछ ऐसे. ui किसको फॉलो करता है? ui को हमने नाम दिया था ना xi माइनस म्यू आई अपॉन सिग्मा आई. तो इसी का स्क्वायर ले लेंगे तो ये आएगा. देखो, इन प्लेस ऑफ दिस आई कैन राइट दिस. सो ये जो स्टैंडर्ड नॉर्मल है ना, तो स्टैंडर्ड नॉर्मल में हमने कन्वर्ट किया, तो ये आएगा कुछ ऐसे, सिग्मा आई एक्स आई माइनस म्यू आई इस पे स्क्वायर और इस पे स्क्वायर dx आई. समझो, क्या ये करेक्ट है? क्या ये करेक्ट है? बिल्कुल करेक्ट है. बस मैंने क्या किया है, देखो mg ये pdf ऑफ नॉर्मल क्या होता है? 1/2 पाई अंडर रूट 2 पाई सिग्मा e टू द पावर माइनस 1/2 एक्स आई माइनस म्यू आई स्क्वायर सिग्मा आई स्क्वायर. यही तो होता है नॉर्मल का, यही तो नॉर्मल का होता है. तो सी अगर मैं यहाँ पे करूं, लेट ui कैपिटल ui इज इक्वल टू एक्स आई माइनस म्यू आई अपॉन सिग्मा आई. तो सिग्मा आई डी यू आई क्या होगा? 1 होगा, क्योंकि अगर हम डिफरेंशिएट करेंगे विथ रेस्पेक्ट टू x, तो सिग्मा आई डी यू आई क्या होगा? x का कितना होगा? 1. सो ये तो कांस्टेंट है, इसका 0 होगा. तो सिग्मा आई डी यू आई होगा 1 इंटू डी एक्स आई. Clear? So now this is minus infinity to infinity 1 upon under root 2 pi sigma e to the power t mu I square e to the power minus mu I square upon 2 और जो ये dxi है इसकी जगह सिग्मा I du लिख लो। ये और ये कैंसल आउट, दोनों तो सिग्मा है ना, दोनों कैंसल आउट। ठीक है, दोनों कैंसल आउट। सो हमारे पास बचेगा माइनस इन्फिनिटी टू इन्फिनिटी 1 अपॉन अंडर रूट 2 पाई ई टू द पावर टी म्यू आई स्क्वायर ई टू द पावर माइनस म्यू आई स्क्वायर अपॉन 2 डी यू आई। क्लियर? यहां तक क्लियर है? नाउ से 1 बाई रूट 2 पाई को हम इंटीग्रेशन से बाहर ले लेंगे। दैट्स 1 अपॉन अंडर रूट 2 पाई माइनस इन्फिनिटी टू इन्फिनिटी ई टू द पावर, देखो यहां से कॉमन क्या आएगा, यहां से कॉमन आएगा म्यू आई स्क्वायर, तो अंदर क्या बचेगा, अंदर बचेगा ये 1 माइनस 2t डिवाइड बाई 2 म्यू आई स्क्वायर डी यू आई। से this is t mu I square minus mu I square upon 2. So this is 2 mu I square minus mu I square, इसके साथ t भी है ना, डिवाइड बाई 2। तो यहां से अगर हम 2 mu I square को बाहर ले लेंगे तो अंदर क्या बचा, t माइनस 1 बाई 2 और ये 2 ये और ये कैंसल आउट, 1 बाई 2 दिस इज 2t माइनस 1 अपॉन 2। तो अगर मैं इसको ऐसे लिखूंगा 1 माइनस 2t अपॉन 2 बट माइनस साइन के साथ म्यू आई स्क्वायर, तो ये तो यही आया ना वापस। ठीक है, क्लियर है? मल्टीप्लाई किया हमने, देखो अगर आप मल्टीप्लाई करोगे ना तो आपको फिर से वही मिलेगा, माइनस 1 प्लस 2t, वही तो है माइनस 1 प्लस 2t। so this is equal to अच्छा, remember here one more thing, the thing is from gamma integral, that if we have function like this is always equal to pi upon a, root pi upon a. So what will be the value of this if this is this? See, in place of a square we have this, and root pi as it is. So can I write this as root pi upon 1 minus 2t divided by 2 1 by 2? Check this. Now can I write this as 1 minus 2t raised power minus 1 by 2? How? What will be the value of see, this is root pi and this is also root pi. Clear? देखो, this is root pi, this is root 2 into root pi, and this is divided by, or this is multiplied by root 2. Why? Because 2 raised power 1 by 2 is root 2. Root 2 cancel, root pi cancel. So this is 1 minus 2t minus 1 by 2. And this is the MGF of chi square 1. So what will be the MGF of, if this is MUI square t, this is the MGF of 1 minus 2t raised power minus 1 by 2. So this is MGF of mu I only. Then what is the MGF of summation mu I square t? That will be equal to 1 minus 2t. In place of minus 1 we have minus n by 2. In place of minus 1 by 2 we can write minus n by 2 when we have the n times mu I. Single mu I, then we have the MGF this. N mu i's, we have the MGF this. So also this is the MGF of This is the MGF of gamma 1 by 2 comma n by 2. Clear? So now, as you know, what is the PDF of gamma distribution? That is 1 upon alpha beta alpha e raised power minus beta x x alpha minus 1. Clear? So this is the MGF of, this is the PDF of gamma distribution. So in place of alpha, write this. In place of beta, write this. So we will get dp chi square, that's the distribution function of chi square, that's 1 by 2 n by 2 gamma n by 2 e to the power minus 1 by 2 chi square, and chi square n by 2 minus 1, where chi square is between this. So this is a chi square PDF. So if we write this in this format, that's f of x, this will be equal to 1 by 2 n by 2 gamma n by 2 gamma n by 2 e raised power minus 1 by 2 x x n by 2 minus 1, and x, when the value of x is between 0 and this. Clear? So this is also equal to 1 by 2 n by 2 gamma n by 2 e raised power minus x by 2 x n by 2 minus 1, and this is this. So this is the derivation of chi square n. This is the derivation of chi square n. Now as you know what's the PDF of chi square n, then if n is equal to 1, we get f of x is equal to 1 by under root 2 pi e raised power minus 1 by 2 x, and this is the x square upon 2 if we use the chi square n. So this is the uh, PDF of normal distribution with mean 0 and variance 1. With mean 0 and variance 1. If n is equal to 2, f of x, that chi square distribution reduces to exponential distribution, with PDF this, and the mean is 2. Remember, in place of n, write n is equal to 1. You will get the PDF of normal, and in place of n, write 2. You will get the PDF of exponential with mean 2. Remember, this is the result, and you can also prove this by putting the value of n in the chi-square distribution function in chi-square distribution function. Now MGF of chi-square distribution. What will be the MGF of chi-square distribution? Let's see. MGF of chi-square distribution. MGF of chi-square distribution. Let x follows chi-square n. What's MXT? That is expectation of e tx, that is equal to 0 to infinity e tx f of xx dx. Clear? So this is 0 to infinity e tx. What is the f of x of chi-square? That is 1 upon 2 n by 2 gamma n by 2 e raised power tx. E raised power tx is this tx, e raised power minus x by 2, and x n by 2 minus 1. Clear? So now this is a constant, so I will be using the gamma integral here, and this term is constant. It will come out from the integral sign. So this is 0 to infinity e to the power tx, and this is gamma n by 2 will also come out, e to the power tx, e to the power minus x by 2, x n by 2 minus 1. So now see dx, say 1 by 2 n by 2 gamma n by 2, 0 to infinity x n by 2 minus 1. And what is this? This is e. If I take x common from here, I will be left with minus 1 minus 2t upon 2x dx. Is it correct? Yes. Now see. Now see. This will be equal to using the gamma integral, but this format. So this is this is like this. The form of this gamma integral is like this: e raised power minus ax x raised power n, and this is equal to gamma n upon a raised power n, gamma n raised power gamma n divided by a raised power n. So this is 1 upon 2 n by 2 gamma n by 2 0 to infinity, or simply we can use here gamma integral, that is, say in place of n we have n by 2 minus 1. Sorry, we have n by 2. This is n minus 1 here. We have n by 2. So this is gamma n by 2 divided by a n by 2. What's a? A is my this. So I can replace a by this, 1 minus 2t upon 2 raised power n by 2. Correct? So this is equal to, when you solve this, so you will get simply this and this will cancel out, and we will be left with 1 by 2 n by 2, 1 upon 1 minus 2t n by 2, 2 n by 2. So this and this will cancel each other. So MGF of gamma distribution gamma n is equal to this, and we can write this as 1 minus 2t minus n by 2, where 2t is less than 1, mod of t is less than 1 by 2. Clear? So this is the MGF of gamma distribution, chi-square distribution, which is also a gamma distribution. See, this is the MGF of chi-square distribution. Now what will be the characteristic function? Simply you have to do one thing. See, characteristic function. Characteristic function. That is simply phi of chi squared t, expectation of EIT chi square. That is nothing but 0 to infinity EIT chi square f of chi square d chi square. And simply using the gamma integral and so on, you will finally get 1 minus 2it minus n by 2 minus n by 2. And one more thing. The thing is that we cannot obtain the probability generating function of continuous distribution. So probability generating function of chi square will not exist. Simply. Now here is a remark. Remark is we have m chi square t, that is 1 minus 2t minus n by 2 As you know, what is this expansion? This expansion is, if I expand this is equal to 1 minus nx plus n minus 1 upon 2 factorial into x square minus n minus 1 n minus 2 upon 3 factorial x cube plus up to, what's the rth term, that's n, or I can write this as up to n terms. So this is the expansion. I am using the expansion this expansion will be used in this. So see how. So see how. So this is m chi square t is equal to, this is c. This is 1 minus x, this is 1 minus 2t. So see, this is 1 plus x raised power n. Then this is equal to this. So see, in place of minus, here is plus. So I can expand this as 1 plus, in place of n, we have minus 2 here. So minus 2 minus is plus 1 plus n by 2, 2t. See, in place of n, sorry, in place of x, we have minus 2t, and in place of n, we have minus n by 2. So this is equal to n by 2, 2t. Oh, sorry, we were correct. This is 1 minus x in place of, sorry, I'm sorry. So in place of n, we have minus n by 2. So minus n by 2 and minus will be positive. That's plus n by 2, 2t plus n by 2, n by 2 plus 1. This is 2t square up to so on. What will be the rth term? The rth term will be n by 2, n by 2 plus 1, n by 2 plus 2 up to n by 2 plus r minus 1. This is 2t r divided by r factorial. Here is it 2 factorial plus up to so on. So now what's mu r dash? That will be the mu is the mean dash. That's the coefficient of t square upon r factorial in expansion. So यहाँ पे जो भी एक्सपेंशन में हमारे पास अगर हमें पूछा गया है म्यू वन डैश निकालो, तो म्यू वन डैश आपको निकालना है. दैट विल बी द कोफिशिएंट ऑफ t1 डिवाइड बाय r1 सिंपली. So this will be equal to, देखो ये क्या होगा, ये होगा n by 2 into 2, that's cancel, this is equal to n. As we know the mean of chi-square is n. So ये तो n मिला ना हमें. क्लियर. सो म्यू आर को मैं ऐसे भी लिख सकता हूं, म्यू आर को भी ऐसे भी लिख सकता हूं इन जनरल. अभी हम कुमुलेंट्स भी देखेंगे, वहां से भी जनरेट होगा. म्यू आर डैश इज इक्वल टू 2r n by 2, n by 2 plus 1, n by 2 plus 2 multiply n by 2 plus r minus 1. So ये कहां तक जाएगा, n by 2 r minus 1. And mu r dash is also equal to 2r gamma n by 2 plus r. This is gamma n by 2 when n is a1. ये कब है, जब n a1 होगा हमारे पास. जब n क्या होगा हमारे पास, a1 होगा. जब n क्या होगा हमारे पास, a1 होगा. जब n क्या होगा हमारे पास, a1 होगा, तब ये होगा 2r gamma n by 2, gamma n by 2 plus r divided by n by 2. एंड गामा 1 by 2 की वैल्यू हमेशा अंडर रूट पाई होता है, याद रखना. अगर हमें गामा 3 by 2 की वैल्यू चाहिए, हम कैसे लिख सकते हैं, गामा 1 by 2 plus 1. तो मतलब ये आएगा, क्योंकि ये आएगा, हम 3 by 2 को बाहर निकालेंगे तो अंदर क्या बचा, 1 by 2. दिस इज 3 by 2 अंडर रूट पाई. ऐसे हम इसको कैलकुलेट करते हैं. यू कैन सी द गामा इंटीग्रल in integration. Follow the integration book that will be easily available in the Google. तो वहां से देख लेना गामा इंटीग्रल को कैसे हम सॉल्व करते हैं. गामा इंटीग्रल को हम कैसे सॉल्व करते हैं. Now see the cumulant generating function of chi-square. Cumulant generating function of chi-square. cumulant generating function. cumulants को generate करना मतलब अगर हमें चाहिए मीन वेरियंस बीटा 1 बीटा 2 वो हम यहां से निकाल सकते हैं. ये होता है बराबर k chi square t. That is nothing but log of mxt, m chi square t, and this is equal to log what is mxt, 1 minus 2t minus n by 2. Now see, using the property of log mn is n log m, so this is minus n by 2 log 1 minus 2t. Now expand this log expansion, that will be equal to minus n by 2. The log expansion will be log 1 plus 1 minus x is x plus x square upon 2 plus x cube upon 3. In place of x we have this, so this is log 1 minus x is equal to x plus x square upon 2 plus x 3 upon 3 plus x 4 upon 4 up to so on. So this is equal to 2t plus 2t square upon 2 plus 2t cube upon 3 up to so on. So see, this is my cumulant generating function. So if I need k1 first cumulant, if I need k1, that is coefficient of t in k chi square t, that will be only equal to n by 2 into 2. This is equal to n. Clear? And k1 is my mean, that's equal to mu I dash, that's equal to n. Clear? Then what is k2? k2 is coefficient of t square upon 2 factorial in kxt, that is equal to my, where is my t square? So this is my t square, that is equal to see this is my t square. इसके साथ और क्या क्या है, ये 2 कैंसल आउट, यहां हम ऐसे करेंगे, दिस इज 2 2 are 4, और simply we can write this as n by 2 into 4 by 2 into 2 factorial into 2 factorial किसके साथ आएगा, 2 factorial इसके साथ आएगा. So 2 4 cancel out, this is equal to 2n. So k2 is my t square upon 2 factorial, that is, क्योंकि इसको ना आपको k2 निकालना है, k2 क्या आएगा 2n, so this is my 2n, and variance is k2, my k2, that's equal to 2n. Similarly k3, that is coefficient of t square upon 2 factorial in t cube upon 3 factorial in k chi square t. See, this is my 2 upon 3 into 3 factorial into n by 2. Wait a minute. K3. If I need kr, what will be the kr? The formula of kr will be n2 r minus 1 factorial. So Kr is equal to K3 is equal to 3, 2 into 2, 2 minus 1. That's 1 factorial. 2 2s are 4, 3 4s are 12. K3 is 12, but K3 is 8. That's K3 is 8n. How is K3 8n? How is K3 8n? Let's suppose we need K2 from this formula. This is 2 into 2. This is 4n. But yeah. Yes. Yes. See, this will be equal to, this will be equal to, this will be equal to 2 2s are 4 2s are 8 n upon 3 into 3 factorial, and this is into n by 2. So 2 1s are 2 4s are 6 4s are 24 n divided by 3, which is equal to 8n. So K3 is my 8n. K3 is my 8n. K3 is my 8n. Now what's K4? What is K4? K4 is equal to coefficient of T4 upon 4 factorial in K chi squared T. That will be equal to, 2 2s are 4 2s are 8 2s are 16 T into 4 factorial divided by 8. This will be equal to 8 ones are 8 2s are. This will be equal to 4 factorial. What's 4 factorial? This is 24 into 2t. That's 48t. Clear? 48t. Clear? Now uh, what is my mu4? As you know, what's mu4 from moments? That's k4 minus 3k2 square. That is equal to what's k4? This is 48n. This is 48n. 48n plus 3. What's k2? What's k2 square? That's 2n. 2 2s are 4n square. That's equal to 48n plus 12n square. Clear? So now what's my beta 1? Beta 1 is mu3 square upon mu2 cube, coefficient of skewness. What's mu3? Mu3 we already know, that's 8n upon what's mu2? Mu2 is mu2 cube. 2 2s are 4 2s are 8. That is this is 8 square n square, and this is 8n cube, which is equal to 8 by n. So beta 1 is 8 by n. Beta 1 is 8 by n. And what's beta 2? That is mu 4 upon mu 2 cube. And this will be simply equal to 12 by n plus 3. Remember this. You can also use beta mu 4 divided by mu 2 cube. So this is the whole cumulative generating function. And remember, this is never be equal to 0, and 8n should be greater than 0. matlab 8n should be always greater than 0. Then this exists. And chi-square distribution, if this happens, then chi-square distribution is positively skewed. This means that the graph of chi-square will lie like this. For different degrees of freedom, the distribution of chi-square will be like this. So you know these cumulants, how to generate cumulants, how to generate moments, that's mu1, mu2 from cumulant generating function. Now there is a property that's known as the reproductive property. Reproductive property. What is this property all about? See, it says that sum of k independent chi-square variate is also a chi-square variate. Now what it mean actually? See, क्या होगा ये? Let x1 square, x2 square, x3 square up to xk square are k independent chi-square variates with n1, n2 up to nk degrees of freedom respectively. Then जो m chi-square t होगा ना, वो होगा 1 minus 2t minus n by 2, as you know. यहाँ n1t मान लो, n1t, क्योंकि अगर हम chi-square 1 की बात करेंगे, ये होगा minus n1 by 2. ऐसी m chi-square 2t 1 minus 2t minus n2 upon 2. ऐसी m chi-square k t will be 1 minus 2t minus nk by 2. Clear है? So if I add up x chi-square 1, chi-square 2, chi-square 3, means that I need the MGF of chi-square 1, chi-square 2, chi-square 3, chi-square k. This will be equal to m chi-square 1 t, or simply plus chi-square 2t plus chi-square 3 up to chi-square k t. As you know from the reproductive property, this will be equal to m chi-square 1t multiply m chi-square 2t up to so on. What is the MGF of this? This is equal to 1 minus 2t minus n1 by 2. 1 minus 2t minus n2 by 2 up to 1 minus 2t minus nk by 2. Clear? So can I write this as 1 minus 2t minus n1 plus n2 up to nk divided by 2. So this is the MGF of sum of all MGFs. That's chi-square sum of all chi-square ones. Sum of all MGF of chi-square ones. That's x1, x2, x3 up to xk, or chi-square 1, chi-square 2, chi-square k. Then the MGF will be this. So if xi square is MGF, x2 square is MGF, xk square is MGF, then sum of these MGFs is also an MGF of chi-square variate. Or we can write this as 1 minus 2t minus n by 2, where n is equal to n1 plus n2 up to nk. This means that if summation xi is chi-square variate with summation ni degrees of freedom. Clear? Clear? This is by the uniqueness theorem of MGFs. Clear? This is the uniqueness theorem of MGFs. The uniqueness theorem applies on this step here. Clear? So in next lecture we will see some properties, some theorems based on the chi-square distribution and limiting distribution of chi-square and recurrence relation.